So let's have a look here at how we can use the instantaneous rate of change to find the max or minimum value of a function. So here we're asked to find the minimum of this function f of x equals x squared minus 2x. And again, we're asked to do this finding the instantaneous rate of change. So step number one here is to find the function that represents the instantaneous rate of change. So let's go ahead and do that. Just a reminder that the instantaneous rate of change, see if I can get this on here. So the instantaneous rate of change is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. So we already have f of x. That part's easy. That was given to us. Here's f of x. So this part is what's going to go in here. We should talk a little bit about what f of x plus h is. So just a reminder, in order to find f of x plus h, we substitute an h into the function everywhere we see an x, pardon me. So f of x plus h means everywhere we see an x in this function up here, we're going to replace it with an x plus h. So we're going to have x plus h squared minus 2 times x plus h. So that is our f of x plus h. Let's substitute that into our equation. Again, we're going to make sure we keep that limit as h goes to 0. Remember, we want to look at what happens as that h value, the distance between the two x values, gets smaller and smaller. So we're going to start with f of x plus h. That's this bit here. X plus h squared minus 2 times x plus h. There's all of that is f of x plus h. From that, we need to subtract f of x, and f of x, I'm going to put some brackets in here so we remember to subtract everything. F of x was this whole thing. So I'll have x squared minus 2x. And all of that gets divided by h. Now at this point, we're just going to expand and simplify the numerator. So we still have this limit as h goes to 0. If we expand x plus h squared, we get x squared plus 2xh plus h squared. So that's just expanding this part right here. We'll multiply this negative 2 through the brackets, and we'll get negative 2x minus 2h. And again, multiply the negative through the brackets here, giving us negative x squared plus 2x. So that simplifies the numerator. That allows us to expand the numerator. And now we go ahead and start to simplify things a little bit. So again, still the limit as h goes to 0. And simplifying, we know that we have a positive x squared here and a negative x squared. So those, we can subtract those and get nothing. And there's also a 2x term over here and a negative 2x term over here. Again, anything without an h should disappear. So all the stuff on the right side of our minus sign should disappear here as it has done. And now every term has an h in it. We're going to go ahead and factor out that h. I know you can factor out more than an h, but we only want to factor out the h. So let's go ahead and do that. That's going to leave us with h times 2x plus h minus 2. We still have our h in the denominator. And remember, the goal here was to be able to divide out the h from the denominator, get rid of it, so that we didn't have an h in the denominator, which would allow us to then make the substitution of 0 in for h. Oops, sorry, h is over here. Everywhere we see an h in this equation, we're going to replace it with a 0. So that means that our function now becomes 2x plus 0 minus 2, which is just equal to 2x minus 2. So that is the function that represents the instantaneous rate of change. Sorry, I got an extra bracket in here or something. That was just a minus 2. All right, we want to know where the minimum of this function is. We know that this is a parabola. It looks something like this. We don't know exactly what it looks like. We could figure it out, I guess, but it looks something like this. And we want to find the minimum value. So we know it's a minimum for sure. We know that the minimum is here, and we also know that the instantaneous rate of change at a minimum is equal to 0. So what that means is that we can take this function now and set it equal to 0. So I'll do that over here. We want to set the IRC equal to 0 to find out where the slope of the tangent is equal to 0. because when the slope of the tangent is 0, we have this horizontal line, and that happens at a minimum or a maximum. So we're going to set the instantaneous rate of change equal to 0. We get 0 equals 2x minus 2. Solve for x by adding 2 to both sides, and then divide both sides by 2, and we get x equals 1. So this gives us the x coordinate of the vertex, or the minimum in this case. We can find the y coordinate by substituting x into the function and finding f at 1. So everywhere we see an x in the function up here, we're going to replace that with a 1. So we're going to get 1 squared minus 2 times 1, which is equal to 1 minus 2, or negative 1. So that, again, this is the y value, this is the y value, and this is our x value. So our minimum then is the point 1, negative 1. And that's how we can use the instantaneous rate of change to find the minimum. You might wonder, why go through all this work to find a minimum when we already know other strategies to find a minimum of a parabola? The advantage here is that this actually works for all functions, not just quadratic functions, and we'll get into some of that a little bit later on. So for example, let's say, and I'll just draw a rough sketch here of a function. Let's say that we wanted to find the minimum, local minimum, and local maximum of this function right here. Well, this function would have is a function, obviously. We can find the instantaneous rate of change of this function, and we know for sure that this function has an instantaneous rate of change of 0 here and an instantaneous rate of change of 0 here. So we could take the function, find the function that represents the instantaneous rate of change, just like we did here, and then we can use that function to do what we did here, set it equal to 0. Now, you'll actually get two answers here. You'll get two x values when you solve, setting the instantaneous rate of change equals 0. So when you do this, you would get x equals one thing and x equals another thing. Now, how do you decide which one is a maximum and which one is a minimum, especially if you have lots of these? Well, that's a question that we should talk a little bit about. Notice here that at the maximum, that's this point right here, the local maximum, the function went from increasing to decreasing. And that's always true at a maximum. So you can see here that the instantaneous rate of change was positive here. The slope of the tangent was positive. And here, the slope of the tangent was negative. So that happens at a maximum. At a minimum, to the left of the minimum, the instantaneous rate of change is negative, and on the right it's positive. So at a maximum, we go from an instantaneous rate of change that's positive to negative, and for a minimum, we go from an instantaneous rate that's negative to positive. And again, that's always as we read the graph from left to right. So we should probably write that down just so that we don't sort of forget or mix it up. So at a maximum, a positive slope, we go from a positive slope, to a negative slope. And for a minimum, we actually do the opposite. We go from a negative slope to a positive slope. And so if we were going to test, so for example, if we took this function that we did up here, we know that it's a minimum. But if we weren't sure and we found this x value and we thought, oh, it's a maximum or a minimum, but we don't know which one, well, we could just choose a value that's less than x equals 1. So we could choose x equals 0, and we could say, hey, let's substitute x equals 0 into the IRC. If we get a value that's negative, that means that the slope is decreasing here. And then we can test on the other side, and then it goes to increasing. If it's going from decreasing to increasing, then we have a minimum value as we wrote here. So that's how we can use instantaneous rates of change to find max and min values in functions.